Hi again. In this fourth video on Unit 5, we will wrap up what you have already studied about carbonyl or alkene insertion. We have seen in the previous classes that oxidative addition and substitution allow us to assemble 1 electron and 2 electron ligands on the metal. With insertion and its reverse reaction elimination, we can now combine and transform these ligands within the coordination sphere and ultimately expel these transformed ligands to form free organic compounds. So let's start with insertion reactions. An unsaturated molecule acting as a coordinated 2-electron ligand, A double bond B, can insert itself into a metal X bond. Remember that X is an anionic 1-electron ligand. In this case, this reaction will give metal bonded to ABX, where ABX is a new 1-electron ligand in which a bond has been formed between AB and both the metal and X. In other words, the insertion reaction leads to a new species, metal ABX, by formation of a covalent bond between AB and X, and the new ligand ABX is a 1-electron ligand, as X. The insertion goes along with a decrease in 2 units of the number of valence electrons and also a decrease in 1 unit of the coordination number, liberation of 1 coordination site. The metal oxidation state remains unchanged. A vacant coordination site is generated, which can be occupied by a new 2-electron donor ligand. Migratory insertions are usually favored on more electron-deficient metal centers. This is a general scheme summarizing the insertion reactions. Remember that R is a hydride or an alkyl ligand. Let's highlight those of the carbonyl and alkenes ligands, but any other unsaturated molecule can undergo this kind of reactions. These are 2 main types of insertion, 1,1 and 1,2, which are shown in this slide. In the first one, known as 1,1 insertion, the metal and the X ligand end up bound to the same atom of an L-type ligand. That is the case of carbonyl ligand, that gives only 1,1 insertion. That is, both the metal and the X group end up attached to the carbonyl carbon. On the other hand, in the second one, 1,2 insertion, the metal and the X ligand coordinate to adjacent atoms of an L-type ligand. This is the case of ethylene, which gives only 1,2 insertion, in which the metal and the X end up on adjacent atoms of what was the 2-electron ligand. The type of insertion observed in any given case depends on the nature of the 2-electron inserting ligand. In general, eta-1 ligands tend to give 1,1 insertion, and eta-2 ligands give 1,2 insertion. These one here are common anionic and neutral ligands that can do migratory insertion reactions with one another. Carbonyl and alkyl migratory insertions are extremely important and are often generically referred to as carbonylation reactions. hydride and carbonyl migratory insertions to produce formyl groups are not common due to the thermodynamic instability of the formyl-metal interaction. These are two different directions that a migratory insertion can occur. A migration, this first one, is when the anionic ligand moves and performs a nucleophilic-like intramolecular attack on the electrophilic neutral ligand. An insertion is when the neutral ligand moves and inserts into the bond between the metal and the anionic ligand. Both of these pathways are illustrated in this slide. A migration reaction involves the anionic ligand doing a nucleophilic-like attack on the neutral ligand. This involves the anionic ligand moving to the site where the neutral ligand is coordinated. An empty coordination site is left behind. An insertion reaction involves the neutral ligand moving over to where the anionic ligand is coordinated and inserting into the anionic ligand metal bond to generate the new anionic ligand. While most systems studied have been shown to do migrations, both are possible. For example, in the case of carbonyl and alkyl ligands, the reason that more electron-deficient metals favor migratory insertion is that makes the carbon atom of the carbonyl more electrophilic and therefore susceptible to nucleophilic attack from the more electron-rich alkyl group. Thus, the migration takes place. But in general, we do not worry about the exact pathway. That is why we use the redundant term migratory insertion to indicate that either directional pathway is fine, and we don't know, or in fact, we don't care exactly how the reaction is proceeding. Many organometallic chemists shortcut this and just say insertion reaction. They do not usually mean that they know what the mechanism is. An alkene and an hydride usually react via a migration of the hydride to the coordinated alkene ligand. In principle, insertion reactions are reversible. But just as we saw for oxidative addition and reductive elimination, for many ligands, only one of the two possible directions is observed in practice, probably because this direction is strongly favored thermodynamically. An alkene and a hydride usually react via a migration of the hydride to the coordinated alkene ligand, as I told you before. The backwards reaction, of course, is a beta hydride elimination and is usually quite favorable if there is an empty orbital cis to the alkyl ligand. Thus, if that beta elimination is to be avoided, it is important to have a ligand or solvent to coordinate to the empty orbital generated from the migratory insertion. Alkene and hydride alkyl migratory insertions are also extremely important, and examples of these two cases are shown in the next two slides, this and the next one. In this one, a 1,2 migratory insertion reaction of ethylene with a metal hydride is shown. In this last slide, the reaction corresponds to alkene migratory insertions in metal carbon bonds. This is the basis for almost all transition metal-based polymerization catalysts. A polymerization reaction is just many migratory insertions of an alkene and alkyl, the growing polymer chain, interspaced with alkene ligand addition reactions. Well, the next and last video of Unit 5 will deal with nucleophilic and electrophilic attack to coordinated ligands. Thank you very much for your attention.